Alright, let's take a minute to review this worksheet real quick. I know there were some problems on here that were maybe a little bit challenging, particularly number 3, but also maybe number 1 part B. So I'm gonna work number 1 and 2 and 3, and heck, let's just do them all. Alright, the International Space Station orbits Earth at an altitude of 380 kilometers. Watch your units on that. We need to be in meters. Has a mass of 4,000 kilograms. The mass of Earth is 5.97 times 10 to the 24th. Usually it's somewhere between 5.97 times 10 to the 24th and 6 times 10 to the 24th kilograms. Doesn't really matter. And Earth has a radius of 6.38 times 10 to the 6th meters. So that unit is good. Calculate the force of gravity on the space station. Okay? The force due to gravity is given by Newton's law of universal gravitation, m1, m2, times g over the radius, or the distance between the centers, squared. So there's the equation, and m1 is the 400,000, right, the mass of the space station. m2 is the mass of the Earth, 5.97 times 10 to the 24th, and g is constant, 6.67 times 10 to the negative 11th, and this is why it all has to be in kilograms, meters, and newtons, because this unit, this is all in SI base units, kilograms, meters, newtons. All right. Divided by r squared. The distance between them squared is the radius of the Earth, which is 6,638,000, plus the distance to the International Space Station, 380 kilometers, which is 380,000 meters, and you have to square that. Okay, so that's just calculator work, and you'll get a force of 3491351.8 newtons, give or take. Okay, it depends on what you use for the mass of the Earth. Okay, so that's a fairly big force. 3,491,351.8 newtons, right? So how fast is the space station orbiting Earth? This seems like, well, how do I figure this out kind of thing. But here's Earth, okay? Here's the space station. It's actually not nearly this far away, and it's moving in a circle. The reason it's moving in a circle is because Earth is exerting a gravitational force forward on it, or not forward, I guess, and it's got a velocity around the Earth. So it has centripetal acceleration. Centripetal acceleration, right? Remember, centripetal acceleration is v squared over r. And the reason it has centripetal acceleration is because it has a centripetal force acting on it. So centripetal force, Fc, is m times centripetal acceleration, v squared over r. And the reason this force exists at all is because of gravity. And so we can take this force, the one we just calculated, and we can set mv squared over r equal to that, 34,91351.8. Of course, then we need m and r so we can get v. Well, we know these things, okay? M is the mass of the space station, so m is 400,000, because it's the force exerted on the space station, not the force exerted on Earth. It's the space station that's moving, okay? V is what we're looking for, so we don't know that one. And r, the distance between them, is right here. It's this radius, so 6380 plus 380 is 676,000, right? That's the distance between the International Space Station and the center of Earth. So you plug all these numbers in and you get 349135.1.8 equals 400,000 v squared over 676,000, and you get a velocity v equals a fairly quick, 7,681 meters per second. 7,681.4 meters per second. Okay, so that's how fast the space station is orbiting Earth. And how many orbits does it make a day? Well, then you got to stop and think, well, how far is it going? Okay, this distance is 2 pi r. Okay, so there's your radius right there, 2 pi times r. That gives you how far it goes, right? And then you divide that by its velocity. 2 pi divided by the velocity tells you how long it takes to make one revolution. Okay, and it's going to tell it to you in seconds. Okay, and it takes quite a lot of seconds. But if you divide it by 60 again, it gets it to you in minutes. It takes about 92 minutes in order for the space station to go around the Earth once. That means it does this about 15.6 revolutions per day. Okay? So it's hauling once around the Earth every 90 minutes or so, about 15, 16 times per day. It's really, really moving. Alright, number 2, this is a much simpler problem. The strength of the gravitational field G. When you see it bolded like that, it's to distinguish it from the acceleration due to gravity, although they're technically the same thing. The acceleration due to a central body's gravity and the strength of the gravitational field are the same thing. Newtons per kilogram are meters per second. So one can be used for the other. So we're given all this information and we're supposed to find the mass of Mars. It's the same equation that we have for gravitational force, right? Except it's been modified a little bit. Since force is mass times acceleration, or if it's weight, it's mg. This is also m times the mass of the central body times g divided by r squared. And since mass is in both of these, we get g, the gravitational field, is equal to the mass of the central body, okay, so whether it's Earth or Mars or the Sun, times g divided by r squared. Okay, and so we're given g, so we have 3.7 equals mass of the central body, which is what we want, mass of Mars, times 6.67 times 10 to the negative 11th, divided by the radius of Mars, which is 3.4 times 10 to the 6th, and remember to square that. Okay? And if you work all this stuff out, then you get a mass for the central body of 6.4 times 10 to the 23rd kilograms. Okay, that's about a tenth, or the mass of Earth, right? If we multiply that by 10, we get 6.4 times 10 to the 24th. Earth is about 6 times 10 to the 24th. So Mars is still really, really big, but Earth is much, much bigger. All right. An enterprising group of students builds a rocket that can achieve a speed of 850 meters per second at liftoff. How high above Earth can it rise? Ignore air resistance. This is a conservation of energy problem. Okay? But the reason it fits in gravitation is because when you launch something at 850 meters per second, that's almost 3 times the speed of sound. Okay? It's going to go really, 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 really high. Now, for things near the surface of the Earth, we've always been able to say kinetic energy plus gravitational potential energy, Ke plus Pe, that we start with equals Ke plus Pe that we end with. But in this case, we got to actually deal with gravity and how it changes, which means we actually have to use Newton's second law Newton's law of universal gravitation when we deal with this, right? Otherwise, we would just say 1/2 mv squared that we start with, right? This would be the old way, 1/2 mv squared plus 0, because it has no height, it's on the ground to start with, equals 0 because it'll get to its highest point and quit, plus mgh. And we would just find h by putting in our velocity here. Masses would cancel, wouldn't matter, and we would get h. Okay, but we can't do that because the further and further and further and further this rocket gets from the surface of Earth, the less and less and less and less g gets. Okay, and so we have a whole nother method of finding gravitational potential energy. It depends on gravitational field and distance. Okay, and so that method is to use kinetic energy plus gravitational potential energy calculated to keep in mind how this distance changes. Okay, and so what we do is we do m of the central body times g divided by r. Now this looks a heck of a lot like, and times the mass of the rocket, sorry. This looks a heck of a lot like Newton's law of universal gravitation. You'll notice it's r instead of r squared. Okay? That's because when work is done on an object, it is multiplied by the distance. Okay? But this is negative. And the reason it's negative is because gravity's pulling one way and we're moving against it. Okay, so kinetic energy minus this potential energy to start with, so this is the starting side, equals the kinetic energy you end with. So I'm going to write Ke2. So up here this was 1 and 1, and this was 2 and 2, and this is 1 and this is 1, minus the potential energy we end with. Now, what changed? The central body didn't change. Universal gravitation didn't change. The mass of the other object didn't change. But the distance, r plus h, that did change. Okay? So now we're actually interested in this h right here. So this becomes a whole lot more complex than just mgh, because we do have to account for the changing gravitational field as you get further and further and further from Earth. But the process is still the same. Kinetic energy plus potential energy equals kinetic energy plus potential energy. Okay, so we're still going to plug in all the numbers. Oh, and the other cool thing is the mass of the object is going to end up to cancel out, right? 1/2 mass of the rocket times its velocity squared minus the mass of the central body, which is Earth, times the mass of the rocket times g divided by the distance that's starting. Okay, so this is actually the radius of the Earth because it starts on the surface of Earth, equals 0 because it's going to get to its highest point when its velocity is nothing, minus mass of the Earth, mass of the rocket, times g divided by the radius of Earth plus h. Okay. Now this looks like a mess, but this mass is here and here and here, so it's gone. Okay, so now I have 1/2 v squared minus mass of the Earth times g divided by the radius of the Earth equals negative mass of the Earth times g divided by the radius of the Earth plus h. Now I'm going to keep that in parentheses so you remember that you have to keep that together because it's on the bottom of the fraction. We can't just start willy-nilly doing some bad algebra with it. Alright, so I don't usually solve and put in numbers until the end, but I'm going to go ahead and put in my numbers. Okay, 1/2 850 squared minus 5.97 times 10 to the 24th, that's the mass of Earth, times 6.67 times 10 to the negative 11th, that's the universal gravitational constant, divided by 6.38 times 10 to the 6th. Okay, equals negative the mass of the Earth, so negative 5.97 times 10 to the 24th times g, I'm just going to write it because I'm out of room, divided by 6.38 times 10 to the 6th, radius of Earth, plus h. Remember that h. This is actually what your unknown is. Alright, so we can do some simplifying because this is just a number, this is just a number, and what we get is negative 520,523,86.36. Okay. 0.36 equals, okay, the top of this is negative 3.982 times 10 to the 24th over the radius of the Earth, which I'm just going to write, plus h. Okay. Now, be careful when you do this, right? You have to multiply this whole thing over here, and that means this number actually distributes. Okay. So, or you have to do the division. So I have radius of the Earth plus h equals negative 3.982 times 10 to the 24th divided by negative 620,523,86.36. Okay? And if you work this all out, okay, then that means the radius of the Earth plus h equals 6417142.4. Subtract off the radius of the Earth, and h equals 37142. 37142 meters. Okay, 37,142 meters up. A tenth of the way to the International Space Station. Okay, so without a nice constant rocket thrust, it's hard to get away from Earth. Okay, all right. Number 4, much simpler problem. The mass of the Moon is 7.3 times 10 to the 22nd kilograms. Its radius is 1,785 kilometers. Again, pay attention to your unit. What's g? Remember, g is mass of the central body times universal gravitational constant divided by r squared. So you just put in your numbers, 7.3 times 10 to the 22nd times 6.67 times 10 to the negative 11th divided by 1785, but remember that's kilometers, we want meters, so 1,785,000 squared, and we get a g of about 1.53, whoa, 1.53 newtons per kilogram. That's also meters per second per second. So what that tells us is 1 kilogram of mass has a force of 1.53 newtons acting on it. So on the surface of Earth, mass is on the moon, mass is accelerated about 1.53 meters per second, about 1/6 the acceleration we feel on Earth. Alright, this problem, not so bad. You just work out the same thing twice. G equals mass of the central body, right? Times g divided by r squared. So you do this once with the distance from the sun and once with the distance from the earth, once with the central body is earth, once with the central body is sun. So for earth I got 0.00263 newtons per kilogram. For the sun I got 0.00593, and you're thinking, wait a minute, if the sun pulls more on the moon than the earth, why doesn't the moon orbit the Earth, or why doesn't the moon orbit the sun instead of the Earth? The answer is it does, right? The moon orbits the sun. We just also happen to be in its field. So the moon orbits the Earth as it orbits the sun. And in fact, the Earth and the moon orbit each other. If you think about it, really, there's a spot between them that they're both going around. And so we're spinning and the moon's spinning and everything's also all spinning around the sun. So it gets pretty complex in a hurry. So the fact that the gravitational field due to the sun is bigger than the gravitational due to Earth at the moon shouldn't be that surprising because we both orbit the sun. Alright. It actually wanted the ratio, and if you do the division there, the ratio of sun to Earth is 2.25. Okay, sun to Earth. So the sun pulls almost 2.25 times as much on the moon as the Earth does. When the moon is in first quarter phase, as shown, this is called first quarter. Actually, that's third quarter. If this side's dark, anyways, doesn't really matter. When the moon is in first quarter phase, as shown, what is the net gravitational field acting on the moon? Well, you just found that Earth pulls this way on it with 0.002 whatever, and the sun pulls this way with 0.005 newtons per kilogram. So you're just looking for the resultant, which is this way, right? You can take this vector, slide it over, so Pythagorean theorem, good to go. And it's like 0.0064 newtons per kilogram. Alright, that's that worksheet. Go through, make sure you have anything there, then we're going to do a quick little quiz, and then we're going to start on thermal energy and what happens to that energy when friction does work.